Hi there, it's Mr. Smith coming to you with a new video about substitution. Now, up until now, we've been studying all kinds of things about antiderivatives and the connection between antiderivatives and derivatives, their inverse processes. And now we're going to talk about a new type of technique called substitution, integration by substitution. And here we're going to take the idea of the chain rule and we're going to see if we can actually figure out a derivative from, or an antiderivative, excuse me, from the chain rule. So we've got a few examples. These go relatively quickly as we go through, but the idea is that we're going to try to see what we can do to undo the chain rule. So what do we do if we have what's called a composition of a function? And the idea is to remember the chain rule. When we took the derivative of something that had an inside function, we needed to make sure that we took the derivative of the outside function first and then multiply it by the derivative of the inside function, leaving the inside alone. So if we ever see anything like we see with this integral right here, where we have an inside function and we have a derivative connected with that inside function, then we can undo that process with what we call integration by substitution. And the idea is that we're going to substitute in a simpler type of function for g of x so that we can actually find the antiderivative a whole lot faster. So here's our first example, the integral of 2x cosine of x squared dx. And the main principle of all this is we're trying to undo the chain rule. So if we can try to find any sort of compositions or inside functions, then that's what we should try to be focusing on. All right, because the idea is if that inside function existed before, when you took a derivative, it added or multiplied something extra to the derivative that we already had. So our idea is we want to try to notice inside functions. So in this case, we notice that the cosine function has a different input. It's not x, it's x squared. So with this knowledge, what we're going to do is we're going to say, let's make u equal to x squared. And this is oftentimes called a u substitution because usually we use the letter u to signify what we're substituting. So when I put u in for x squared, this integral now becomes the integral of 2x cosine of u dx. Okay? So we're not done yet, but the idea is, okay, well, we've made the inside function a little simpler to work with. So the second part is to recognize what the derivative of this substitution is. So here we made u equal to x squared. So du dx, the derivative with respect to x, is just 2x. Now, if we multiply both sides by a dx, that means that du equals 2x dx. Now, there are a couple different ways that we can go from here. I think the maybe simplest way that we can do this is to solve for dx because it's something we need to get rid of in our integral. We got rid of the inside function, and now we've got this dx. And the whole idea is we want to substitute so we get rid of all the x's and convert everything that was an x into a u. Okay, so what I can do is I can solve for dx and say du over 2x is what dx is. So going back to what we already substituted, so we have a cosine of u, and we want to get rid of that dx. Okay, and when I do so, all right, I get the integral of 2x cosine of u times du over 2x. That's the substitution we just created. Now, if you made a good substitution, you should notice something happens almost immediately, and that is that the 2x cancels out with the 2x here in our numerator and denominator. So all you're left with is the integral of cosine of u du. And the idea is that this is a whole lot easier integral to try to solve than the integral that we had before. We don't know what's going on with that x squared, but we can find the integral of cosine of u du. That integral is just sine of u plus c. And then once we've actually gone through and made the substitution and found the integral, we can plug u back in. All right, it's like a body double or something, like a stunt double in one of these movies. All right, the u is going to make the whole movie go a lot better because we've got a better stunt double to come in and actually do the stunt. And the stunt is taking the integral. And once we're done with that, Tom Cruise or whoever it is comes back in. All right, u equals x squared. And so we substitute that back in and we've got our antiderivative. And again, you can always take the derivative of our antiderivative and it should match what the integrand says. So in this case, when I take the derivative of sine of x squared plus c, I'm going to get cosine of x squared times the derivative of x squared, which is 2x, which matches what I have up here. Okay, so here's another example. We've got the integral of 4x minus 1 to the 5th dx. So remember, focus in, laser focus. Do you have some sort of an inside function in here? And we do. We have 4x minus 1. Looks like it's plugged into something to the 5th. So what we're going to do is we're going to let u equal to 4x minus 1. All right. If that's the case, then du dx is equal to 4. Du is equal to 4 dx if we multiply both sides by dx. And then du over 4 is equal to dx if we solve for the dx part. Okay. And now the idea is we've got something that can go inside to the fifth function. All right, so we call this u to the fifth. That's what 4x minus 1 becomes. And then we know what the dx is. That's just du over 4. Now remember, one of our rules about antiderivatives, all right, is that we can pull out any sort of constant. So I'm going to pull out a 1/4 here. And so this is just 1/4 times the integral of u to the fifth du. The antiderivative of u to the fifth is u to the sixth over 6. When we multiply that by a 1/4, we get u to the sixth over 24. So this is a much easier integral to work with. And then, of course, our plus c. Once the stunt has been taken place, then we can put u back in, and we get 4x minus 1 to the sixth over 24 plus c. All right, so here's another one. The integral of x squared times the square root of x cubed plus 1 dx. Do we spot any inside functions? Do you see it? Does it look like we plugged something into another thing? Indeed we have. Here u can be x cubed plus 1, which would mean that du over dx is equal to 3x squared, which makes du equal to 3x squared dx. So get used to, by the way, jumping right to this step here. That's the derivative with a dx attached to it. We're just moving that dx over. And so dx is equal to du over 3x squared. So now let's do some substitutions. So I can plug in u equals x cubed plus 1. That goes into the square root. And then I can plug in for dx. dx is equal to du over 3x squared. And what I want you to notice is that the x squareds go away. And so we're just left with, inside the integral, 1/3 square root of u du. And as always, we can pull our constant out right here. So take a moment, make sure that you understand what's going on here. The x squared's canceled, and now we're down to the integral of the square root of u du. Once you get that, the antiderivative of u to the 1/2 is 2/3 u to the 3/2. That's our earlier lesson on antiderivatives. And then multiply all that by the 1/3 out front plus c. So we end up with a 2/9 u to the 3rd plus c. And then our u gets plugged back in, so we get 2/9 times x cubed plus 1 raised to the 3/2 plus c. All right, what about this one? The integral of 2x e to the x squared dx. Now, exponentials are a little bit trickier to see what your inside functions are, but we've plugged in x squared into our exponential function. That's our new input here. All right, so what we do is we can say, well, u is equal to x squared. So du dx is equal to 2x, and dx is equal to du over 2x when we solve for dx. And now when we substitute, all right, this becomes an e to the u because x squared is equal to u. And then we get a 2x and a du over 2x. That's what dx is equal to. The 2x is canceled, and so this is just the integral of e to the u du. When I integrate, I get e to the u plus c. U is equal to x squared, so we plug that back in, and so our antiderivative is e to the x squared plus c. All right, what about this thing here? What's going on with this? So we've talked all about how finding inside functions are an important part of doing a substitution. Another important part about it is that has kind of gone swept under the rug here is we can find a function and its derivative usually in an integral where substitution is appropriate. So this integral right here is the integral of arc sine of x over the square root of 1 minus x squared dx. And the question is, what in the world do I do here? Do I make 1 minus x squared my inside function? What do I do? Well, another technique that you might find helpful if you get stuck is to say, well, do I see a function and its derivative inside the integral here? And the answer is yes. If we were to make u equal to arc sine of x, then du dx is actually that 1 over the square root of 1 minus x squared. All right, so that's why we see that here. And so if we manipulate this and solve, we cross multiply, we get dx is equal to du times the square root of 1 minus x squared. And now when I do a substitution, I notice that u is the inverse sine of x part. All right, and then dx was the du over the square root of 1 minus x squared, which will cancel with our denominator. That's key there. So all this reduced down to the integral of u du. All right, so the trick was to notice, hey, was there like a derivative that matched something else that was an inside function? And going back to some of these old ones, you see that we've got x squared and its derivative 2x in the integral. If we look back here, x cubed and a form of its derivative, which was 3x squared in the integral. That's why it worked. If we look back here, let's a good example. So if we look here, we got x squared as an input and then 2x as a derivative in the integral. So that was the key to this one. As we went through and solved it, we said, oh, the derivative of inverse sine was in our integral. And notice we got this nice easy integral to work with, the integral of u du. Well, what do we do with that? Well, that integral is just u squared over 2 plus c. All right. And so once you've done that, once you've done this stunt with a whole lot easier stunt double, someone who knows how to do it, all right, now you can just go and plug in u equal to inverse sine of x, and you get inverse sine of x squared over 2 plus c. So in summary, integration by substitution finds integrals by undoing this chain rule process. Some keys to doing it: try to find an inside function. If it looks like it's composition, like you've composed it, make the inside part your u. If you see that the derivative of one part of the integrand is also within that integrand, then make that your u. So two things that are working in conjunction to help you decide what your u is. And then you've got a du already in the integral. So solving for dx and substituting it is really important there. Thanks for listening, and we'll see you on the next video.